Thank you, everyone. I want to thank the Coastal and Heartland National Estuary Partnership for inviting me and giving me this catchy title. Um, and as you can imagine, I'm going to talk about the extreme heat or heat in general or warming temperatures. Fortunately, our esteemed, state climatologist David Seaton covered some of the stuff that I was going to cover. So maybe I can gain some time. I can try to skip some of the material or discuss in lesser detail. So I will be talking about the trends in warming, and more importantly, how would this affect in the water and the wetland environment. So I will focus on maybe the local wetland, some study that was done, and also more importantly, how would it impact, particularly in terms of projections into the future for systems like the Everglades. Next slide, please. I think it's a good place to start with the hydrologic cycle. Many of you hydrologists are very familiar with this. Basically this movement of moisture and water in the land phase of the Earth system. I have listed here primary variables of interest to us in this hydrologic cycle: temperature, precipitation, and something intimately connected with the temperature is evapotranspiration or water losses, which is important for water supply and wetlands in general. And I will focus on that a little bit. I'm not going to talk about sea level, which is what I typically talk about, but not today. But they say that maybe the hydrologic cycle can be on steroids. In other words, with the warming. We know that the warmer atmosphere can hold more moisture and could result in higher extreme precipitation, and with higher temperatures, it will cause more water losses from the system. I can tell you that, based on our experience, the climate models are pretty good in predicting temperature, but not so skilled in precipitation. And you will see that why we have to be thinking about that, the lack of scale. So this has implications for ecosystem, human health, water management, energy, agriculture, and economics. And I will touch on some of them, but not all of them. Next slide, please. So another way to look at this is, in general, the Florida's water resources system. I think on the first panel, you see some of the drivers, and I think David talked about this already: rising sea levels and groundwater levels. I think Scott talked about the groundwater level rising as a result of sea level rise. The one that I'm going to focus is on increasing temperature and evapotranspiration. I will not talk much about changing rainfall and tropical storms, which David also touched on. So when you look at the water management impacts in Florida, in South Florida in particular, there are 4 types of impacts I have identified: a direct landscape impact due to storm surge and maybe king tide flooding that we heard, water supply and stormwater intrusion that Scott talked about, flooding and natural system. The important point is on the right-hand side, the last panel. We've been planning systems, bigger, large-scale planning projects using what we call stationarity. And this paper you see on the bottom right-hand side is fairly well known for highlighting this question of, is stationarity a still valid paradigm? And we've done a lot of work on non-stationarity, and I think that's where we are heading in terms of planning. Next slide, please. David already showed this, some of the information, but this data is available from the NOAA, and you can pretty much develop a temperature record. So the data, as David mentioned, is already showing a trend, increasing trend, particularly since about 1980 in many parts of Florida. And the precipitation signal is now very clear. We do have decadal, multi-decadal cycle. That is also important for water supply. And I would argue that we cannot look at temperature without looking at some of the other drivers. And I think, Jennifer talked about compounding effects. So I think I'm going to touch on that as well. Next slide, please. So this data came from South Florida Water Management District. They looked at all the measured pan evaporation data. And we have, what you're seeing is from 1961 to 2019. This is the pan ET data. They're already showing some trends. And in their report, what they're suggesting is that we have already seen an increase in pan ET, indicating perhaps we are losing more water compared to the past. And I think, we don't have a whole lot of data on ET over a long period of time. I think this is one set that's useful. Next slide, please. So this is, I think David touched on this too. And, basically the impact of increasing heat on health. And this is from this document that you see on the lower left-hand side from one of the organizations that looked at the heat, not Climate Central, Union of Climate Scientists. What they did was basically come up with some thresholds: 90 degrees Fahrenheit, 100 degrees Fahrenheit, 105 degrees Fahrenheit, and off the charts category there. And then basically categorizing the heat index, which is a function of both temperature and relative humidity, as you can see. But you can see on the upper left-hand panels, there are different thresholds, have different implications for humans. Basically, about 90 degrees, outdoor workers will be more susceptible to heat. About 100, the elderly and the children and women and people with underlying health conditions are at risk. About 105, almost everybody is basically affected by this increasing heat index. Now, what you see on the upper right-hand side, the heat index is useful for certain situations, like in shaded areas, for example, but in reality, for heat stress under outdoor conditions, for example, when you have sunlight on people working, you really need to have other variables incorporated. For example, wind speed, solar radiation or sun angle, and cloud cover, and humidity, as in the case of heat index. So unfortunately, there's a measure called wet bulb group temperature, but that data is not readily available. It's beginning to come. That is actually what we would need in the future to look at the impact of heat stress on human. And I know there are a couple of talks, or maybe at least one talk on human health later on, and I will skip the rest of it now, and please move the slide. David also covered this. One thing I want to highlight, and he showed this data, the nighttime temperature is increasing faster than the daytime temperature. You see the southeast Florida is the nighttime temperature increase. This is, again, is from the National Climate Assessment. And what they said was 61% of major southeast cities are exhibiting some sort of worsening heat waves. And hot days and warm nights together, human comfort, particularly the energy requirement. Agriculture is affected. And there are many other implications of this increasing heat. But later on, I will focus on the sort of the water budget aspects of increasing heat. Next slide, please. So the projections are hard to come by, and this particular information from the Union of Concerned Scientists, they have GIS map for the entire country, and including Florida. All congressional districts have this information. So what they did was the heat index about those threshold 90, 100, and 105. What is the general number of days above that threshold for under historical condition? As you see the years in there, the mid-century and late century. And they also had a column what is called here by late century, if we limit the 2 degree temperature increase. To give an indication to the public, the importance of mitigation. What I'm finding interesting here, and this is only for the couple of counties in Florida, and it can be available for any other county. You can see under 90 degrees, the increasing number of days is to mid-century is only about 30 some days. But when you go to a higher threshold, the increase is much larger percentage-wise. I think this is a significant result in terms of what to be expected in the future because of this increasing heat. Next slide, please. So we've been looking at future. I mean, my focus is primarily on future projections, climate data. And as I mentioned, temperature has a better skill in projecting future temperature than precipitation in climate models. This is, I call this latest, but it's really not the latest. This is based on CMIP5 or the class of models that some of you are familiar with. You can see that the panel on the left, you see all the data and then sort of a smoothing of that data over the years from historical to future, the significant increase, very consistent increase in temperature and the spread you see for different climate models. So they all have similar order of magnitude. So this is useful for picking some scenarios of warming when we look at impacts on the water budget, for example. What you see on the right-hand side is the change in seasonality. To me, this is a very significant result because when you look at the future condition, there are 5 models highlighted in there. You can see the length of the summer season increasing by several months. And you can imagine the implications for energy requirement in the future when you look at this, the length of longer summer months in the projections. Next slide, please. So there is an interesting spatial trend in the state of Florida. And you see on the left panel, I put both temperature and precipitation here. On the right-hand side, again, for a different class of models called CMIP5 or model data sets, there is CMIP6 data that we have not looked at it. They're consistent in terms of the trend pattern. What you're seeing is from south to north in state of Florida, from Everglades to all the way up to north in latitude, you see an increasing trend, increasing warming, which is something that I think David also showed when you look at North Florida. And you see both the types of climate data sets show similar trend, but the exact magnitude are a little different, about 1 to 1.5 degrees or 2 degrees. And so this is an interesting consideration that we need to think about when we look at North Florida versus South Florida. In the precipitation pattern, you see a drying in the south in the CMIP3 data, but you don't see that in the CMIP5 data. So this is one of those uncertainties I discussed earlier. You really need to look at a scenario approach in terms of looking at these variables because climate models are not perfect yet in terms of projecting the future conditions. Next slide, please. So this is only one slide I have. On a wetland condition, this is an interesting paper that was published actually this year. This is a controlled experiment in China. And what you're seeing here is that what they did was they actually artificially warmed these plots to see what kind of effect that has on the primary productivity of these wetlands. So they had a control and with warming condition. And you can see the upper right hand, there's a little panel showing the increasing soil temperature. And what they found was the climate warming can significantly reduce wetland resistance and resilience to flooding events. And resistance is what they define as the ability for the ecosystem to maintain its original level of productivity during extremes. And the other resilience is more like a rate at which they will return to the pre-extreme level. In other words, basically the resilience of system returning to some pre-event condition. They also found the warming can rapidly alter plant community structure and found that there are other implications on the carbon processes in the system itself. You see the lower right-hand figure showing the change in resistance and resilience under warming. Next slide, please. So I'm going to talk about something I had done actually some years ago. So the question was, so what is this changing temperature, precipitation, and sea level rise have on a system like the Everglades? This was done through modeling. So based on the projections I picked up, average temperature increase of 1.5 degrees, precipitation because of that uncertainty, I picked at -10%, +10%, and sea level rise 1.5 feet on the time. What you see on the upper right-hand side is, so what does that mean to evaporation losses from the system? And what we found out with some limited modeling we did, that ET increases by about 7%, the potential evapotranspiration, because of the 1.5 degree increase. And we found because of the temperature or precipitation changes, we saw significant decrease in inflows to Lake Okeechobee. So these are important factors for future viability of water supply, whether it's due to temperature increase or precipitation. Next slide, please. So what we found, you see on the left-hand side, Lake Okeechobee stages, and we ran several scenarios, the base condition, plus rainfall, plus ET, minus rainfall, plus ET, and so forth. You see the rainfall seemed to have a lot bigger impact in terms of lowering the water level in Lake Okeechobee, primarily due to that decrease in inflows coming into the lake. And on the right-hand side, right-hand panel, you can also see the seasonal contribution to the Everglades National Park under these climate scenarios could be significantly different. As you can see, the seasonality change and also magnitude changes. Next slide, please. So a couple of maps before I conclude. On the left-hand side, what you're seeing is what happens to the Everglades system and the increasing ET scenario. And you see the blue on the right-hand side is basically these are all water level maps. The blue on the right-hand side is basically with increasing temperature, you also have increasing sea level rise. That's one of the assumptions we had. So you have a increasing groundwater levels, but actually drying of the Everglades. But when you couple that, as you see on the right-hand side, with decrease in rainfall, implications are a lot more significant, particularly in the Everglades in terms of drying. Next slide, please. You see the left-hand side, the same map showing decreasing rainfall and increasing ET. So what if you had a higher rainfall with higher increasing ET? Seems like the increasing in rainfall, if it's realistic or if it is real, could probably overcome some of the losses due to ET. You can see from the water levels. And we have included the sea rise in both scenarios. That's all what I have. I think the next slide is the question slide. Florida becoming a monsoon region instead of semi-tropical with drought flight cycles, but less fierce hurricanes. Rising heat index makes more drought conditions down here. Well, I'm not sure about the less fierce hurricanes. I think the projections are that the category 3, 4, and 5 could be increasing in frequency, and maybe the rainfall will increase. Rising heat index, I think, I don't know about the drought condition. You saw the ET increase, could create more water losses, so water management becomes important. On the right-hand side, the question, will planting more trees help reduce warming? Clearly, locally or hyper-local condition, that could significantly improve the heat impact on communities by having trees in the neighborhood. I think the people are working on that already. I think that's all the questions I have.